All right. So we are 1 minute to 9:45. Okay, let's start. So today we are going to do 3 problems, and we are going to verify that the answers we do on paper matches with the results in Simulink. So I hope you all have your laptops, so we could. I think was the model file uploaded on Moodle? You have the model files? I hope. So I think we'll straight away open the model file in MATLAB and then modify that file from there and then do the first problem. So if you could please open your laptops and open that model file from Canvas on MATLAB. You don't have your laptop?
I only actually have a desktop.
Okay, got it. You don't. All right. So then it makes the job easier for me. I will just show you the modified file on my laptop, and then maybe you guys can follow the same modifications and simulate it and try it out. So the first problem that we will be doing is the converter redesign. So in the Simulink model, if you can see my laptop, I have a DC bus voltage of 5000 volts and an RL load of 10 millihenry and 50 ohms. So we need a power out. So the load cannot be changed. The value of the load is not in our hands, and we want a power output, active power of say 5000 watts and reactive power of say 400 volt ampere reactive. So the question is to give this power to the load. So what would you do if you have a fixed RL load? Say this is 50 ohms, this is 10 millihenry. Say this is not there. There is no other AC source connected. And we want to feed a power of 5000 watts and 400 volt ampere reactive to the load. So the only thing that we can control really is this point's voltage VO, and we can also control the voltage output of these submodules here, and this we know is VL, this we know is VU. So we know, ignoring the drop across this arm inductors and resistors, assuming it's small in the simulation, it's 0.1 ohms and 0.5 millihenry. So in this problem we'll ignore the effect of that, but we'll take up the effect of that in one of these problems. So ignoring the drop across this, what will be VO? VO we know is VL minus VU by 2. And VL has a waveform that looks like this. It has a VDC by 2 average and an AC voltage. So the AC voltage is actually VO peak to peak. This is VDC by 2. So the modulating signal that we will feed to each of these submodules, let's call that M. That will be some 0.5 plus MA sin omega t plus alpha. So M times VC average is submodule output voltage. Okay. Now if you look at the simulation uh, is built in such a way that the modulation signal goes from +1 to -1. It has no DC bias and it is being compared with triangles from -1 to 1. So what I mean is the triangles go from -1 to 1 and the modulation signal also goes from say some peak value MP to -MP. Now we can in this case this is equivalent to comparing it with a triangle from 0 to 1 and a modulating signal going from 0 to 1 also. So what you do is you multiply this by 0.5 and add 0.5. Similarly multiply this by 0.5 and add 0.5, and since we are comparing these two and doing the same operations, these two things are equivalent. So multiply each by 0.5 and add 0.5. So this form of the modulating signal is useful in finding out the voltage of the submodule with respect to submodule's negative bus. That will be this M times VC average. So it will have a V. So the minimum that this point's output can go with respect to this DC bus point is 0. So we have a 0.5 offset. But if you want to know the output voltage here with respect to ground, which is the midpoint of the DC bus, we could use this signal directly. Let's say this M dash with a peak of MP, then M dash times VDC by 2 is VO. And we give the same M dash to the lower arm submodules and upper arm submodules. Okay, so that's in short, all that I am saying is the modulation index that you see on your Simulink model, this modulation index multiplies VDC by 2 to give the output voltage.
I have a question. You say that you draw the waveform called modulating signal and you multiply it by 0.5 and then you add 0.5. So how does that become 1 to 0 on the right? How do you find that?
So this becomes, if you multiply by 0.5, it becomes minus 0.5 to 0.5, and you add 0.5 to this, it becomes 0 to 1.
Yeah, that I understand.
And then similarly, if this has a peak of say 0.84, and I multiply by 0.5, I get 0.42 to minus 0.42, and I add 0.5, I get 0.92 0.92 to plus 0.08. So then I compare this with this.
Okay. But you know, my question was you wrote down 0 to 1 on that waveform.
Yeah, that is if this is this is 1 and minus 1, 2.
Then it makes sense.
So the form of the modulating signal that we use is important in deciding what output voltage we are finding out. So this form is useful if you want to find the output voltage with respect to submodules negative bus, and this form of modulating signal is useful if you are finding output voltage with respect to midpoint of submodule. Do you know why? Because if I compare the modulating signal that goes from -1 to 1 with -1 to 1 triangle carrier, then it's like I am probing this modulating signal with this triangular carrier, and suppose this was so in that case, if I want to say M dash times DC bus, m dash times, for example, m dash times VDC over 2 is VO. So, if m dash is minus 1, VO is minus VDC by 2. If m dash is plus 1, VO is plus VDC by 2 with respect to this ground. Whereas if I use m times VC average equal to V submodule output, m at the minimum is 0, at the maximum is 1. So with respect to submodule negative bus, it can only go till 0. So I think if you think about it a little bit, you will understand that this m dash times VDC by 2 is VO.
And this VC average is the voltage across the capacitor?
Yes, sir. Submodule capacitor voltage.
And this VSM
Output is this is the submodule output voltage. Submodule output voltage.
for any submodule.
Yes, sir. With respect to negative of submodule. So this VO peak to peak, the sinusoidal waveform, so this is VO, that is actually m dash times VDC by 2. So this is VL, right? So if you look at VL, at most it can go as much as VDC, and at the least it can go as much as 0. We talked about this last class. So if m dash is 1, VDC by 2 plus VDC by 2 is VDC. If m dash is minus 1, VDC by 2 minus VDC by 2 is 0. Okay. So in short, when we compare a modulation signal with minus 1 to 1 carrier, the peak of the modulating signal times VDC by 2 is the output voltage, if you ignore the drop across the arm. Let's take it at that. And I have explained that point as much as I could, I think, and we should move forward. So then we need to find the modulating signal m dash, which is equal to, say, ma sin omega t plus alpha. That will give us this power. Okay, that power and that Q. So let's find out the equation for power. I have the equation P and Q written down there, but I will derive that here. So what is VO? VO is ma sin omega t plus alpha times VDC by 2. We have that, and then what is IO? IO is VO by R plus JXL. So what is real power in phasor? So what is this in phasor quantity? That should be MA VDC by 2 angle alpha by rho 2, because we take RMS quantities in phasor when we deal with phasors. What is IO? IO is MA VDC by 2 by rho 2 angle alpha divided by R plus JXL. Okay. So what is P now? P is real part of, okay, let's write S. S is VI conjugate, which is equal to MA VDC over 2 by root 2 angle alpha times MA VDC over 2 angle alpha by root 2 by R plus JXL the whole conjugate. So if you put in numbers here, you get MA times 2500, which is VDC over 2, and you have angle alpha by I take the root 2 times root 2 as 2 outside, and then again I have MA times 2500 angle alpha. So let me expand the angle alpha part. Write this as MA times 2500 times by 2 times cos alpha plus j sin alpha times MA times 2500 times cos alpha plus j sin alpha by R plus jxl the whole conjugate. And then what you do is multiply numerator and denominator by R minus jxl here. If you do that, you get P as MA times 2500 by 2 cos alpha plus j sin alpha times MA 2500 cos alpha plus j sin alpha times R minus jxl by R squared plus x squared the whole conjugate. You expand this out and then you get this answer. So 0.3 here is MA and 20 is alpha. So I have taken MA to be 0.3, alpha to be 20 degrees. So you get, so MA, so P is 0.3 times 500 times cos alpha. So this is real times cos alpha times R by R. So first term is real here. So you have MA cos 20 times RL, the whole divided by RL squared plus XL squared. Then you have you can expand this out and then take the conjugate. So
You're trying to solve for
MA and alpha.
and alpha, right? So you have two equations that you have.
Yes.
So that's a complex equation.
Yes.
So given P of 5,000, Q of 400, right?
Yeah.
So you
So,
can just
yeah.
that's the answer you got.
Okay.
They can check whether the right one.
Okay. So with this MA of 0.3 and alpha of 20, I get P to be 5,500 watts and Q to be 420 VAR or something in that range. Approximate. Just choose an alpha and M and see if it is close with.
But if they have two equations,
Yeah, we can exactly solve for.
solve it exactly.
Yeah. Yes. Yes.
For MA and alpha.
Yeah. So I.
Leave it at that.
Yeah.
Sure.
So that's what I did. So in the Simulink model, I set MA to be 0.3 and alpha to be 20, and you can. Yeah.
Two questions. One is the solution that you have shown requires the value of load to be known, right?
Yes.
Second question is, does it take into account the R inductance?
No.
It assumes a 0 or it's negligible.
Yes.
Okay.
So I add in the power block here, and then So Simulink does everything for you. You just need to plug in M and alpha and see if the power matches. I think so the next question is, so if I choose an M of 0.3, it's not a very good operation of the MMC. Nobody operates the MMC with such a low modulation index. Do you know why? The reason is this. You will see that so if I go to sync here, sync and display, and then I run this. So can you guess why? Why don't we operate MMC with modulation index of 0.3? No, if I say the answer, then it won't be as good as viewing what the answer is on Simulink. I mean, I will show you the waveform and then you tell me why we don't do it. So
you don't design
yes, sir.
for that low an MA.
Yes, sir.
You may
Yeah.
operate that there if needed, right?
Yeah, we can operate, but we don't design.
Design, the
Yeah.
rating would be much higher MA.
Yes, yes.
And MA can be as high as 1, right?
Yes, sir. Can be. Yeah. So. If you look at the output waveform here, we have 4 submodules per arm. So how many levels do you see here? Totally, you have 1, 2, 3, 4, 5. 5 levels. How many levels do we know we can get with 4 submodules per arm? 2 and yes, 9, right? So we are not using all levels. So this is a very poor output voltage waveform. It has higher harmonics. Do you know why we only get low levels?
I guess it has to do with the low modulations.
Yes, that's correct. So if we have only 0.3 as modulation index, so 0.3 times 2500 is how much? It's less than so 0.3 times 2500 is the maximum voltage here, right? It's point 750. Yeah, maybe the fundamental waveform here is 750 volts, but 0.3.
Because it's switching the nearest levels, right?
Yes. Yeah, so maybe the fundamental voltage waveform here is 750 volts, but we don't. But we know for sure that we don't go till plus VDC by 2 that we saw last class. It used to go till how many levels did we have with 4 modules? We had plus 2500, plus 1250, and 0, minus 1250, and 2000 minus 2500, and one level here, one level here, one level here, and one level here, right? Right? Average of this and 1250 here will give a level in between 2500 and 1250. So we have 9 levels, 4 here, 5 here, plus 4, the 4 levels in between. So we used to go till 2500 at most. We don't go till there because we don't. we can't afford to go till there, because if we had gone till 2500 to produce a lower fundamental voltage, we still have large harmonics, because we need the level closest to the output voltage, right? So how will you, so the next question is, how will you redesign this converter? How will we redesign this converter for a good output voltage profile and current profile?
So another reason, if I may,
Yes, sir.
yes, is that you get such a low voltage of 750
Uh-huh.
with MA of 0.3. You're using devices which are seeing way too high a voltage, right?
Yes.
So why waste the rate
Exactly.
of these devices, right?
So that is the direction in which we want to redesign the converter. So what do we know for sure? We know that if we have a high MA, say 0.8 or 0.9, we use all the levels, right? If you have 0.9 times VDC by 2, then we will go to 2500 and the level just below that, this level. So what is that? Say 17 something. How much was it? 1725 or something? And then this was some 6, yep, and minus 625 and minus 1725. So if you had 0.9, so if you had m dash of 0.9, the output voltage would have been m dash times 2500. So then to produce this, we would switch between 2500 and 1750. So then we would get all levels. And some lower, and if you get to this point, then for lower m is a sinusoidal, right? So for all other m, we would go through all other levels. We get a, so if you look at the current waveform here, you see that it has higher harmonic content right there. We could get a purer sine wave current at through the load. So how will we design this converter so that for this power we get, say, m dash of 0.9? Okay, so what will we do? So 0.3 times 2500 should be equal to 0.9 times VDC over 2. This is our new VDC over 2. So VDC over 2 should be 2500 by 3. So then VDC will be 5000 by 3. So the DC bus goes 1/3. If the DC bus goes 1/3, you also have to redesign the capacitor voltages, right? Capacitor voltage ratings. So they all go 1/3. So VC will be what? 5000 by 3 by 4. Okay. So what you can try is go home, open the model, change VDC, VC to these values, and see if you get a better sine wave through the output. And now the modulation index is 0.9. And what do you think the alpha will be? If I had chosen this alpha to be 20 degree, what would be the new alpha? All we are changing is the magnitude, right? I mean, the output voltage magnitude should remain the same. So the phase angle should remain the same as before, don't you think? So after you redesign VDC and VC, if you change MA to be 0.9, you see that there's a better sine wave through the output. Okay. So the main solving that is involved here, I don't know how. Our main solving that is involved here is finding out MA and alpha, and then once you do it for this case. Yeah, you do it for this case, for this R and L, and yeah. That's the first question. We can go to the next question now.
Is this a homework problem?
Uh,
What you're discussing is a homework problem.
it was all three problems are meant to be homework problem.
And when are they due?
Uh,
A week from today or something like that?
yeah, week should be a good time, I think.
So a week a good time?
So, I mean, are we going to get like an assignment and like the questions and everything?
Uh,
Yeah, you will write up these problems, right?
yeah.
Right. So DAB problem is due when? This Thursday? This coming Thursday. So there's one assignment that's coming due this Thursday, having to do with this we talked about, dual activity, right? And then this one, if it's due a week from today, or it could be a week from Thursday, right?
Yes, sir.
Because there's no final exam. So it could be a week from
Yeah, that's fine. I mean, I just want to like have an actual, like have the questions.
yeah, it'll be written.
Yeah. Okay, cool.
There'll be, he's just making some assumptions here and things like that, but they'll be tightly written up, okay? And you have to just modify these simulations.
Yes.
That he has given. That's quite a bit of information, as you can see, in 3 lectures from very start to actual modeling and then calculating and analyzing and assembling. A lot of information in 3 lectures.
Question.
Yeah.
So I see why we changed the DC bus voltage, and that seems easier than modifying the 50 ohms and 10 millihenries. But could you modify that at all to change your?
You can, but this problem is such that the load is not in your hands.
Okay.
Load is you have a fixed load given to you.
It's given. You're saying that load is given.
Yeah.
P and Q are given.
Yeah.
What do you do, right? So once P and Q are given, load is given, then that voltage is pretty much specified, VO, right? In terms of magnitude and phase angle.
So
Sorry, one question. If load is specified completely in terms of R and L, how can you specify P and Q together?
Because you control the voltage, right? No?
You
Yeah.
can only control the voltage, right? I mean, if you control the magnitude of the voltage, then P and Q are determined by L and R, right?
you can control the magnitude and phase angle. So if you
Phase angle with respect to what?
phase angle with respect to ground or with respect to impedance angle of the load. Phase angle with respect to 0.
Well, my argument to that is, could you say this load is given, and I say P of whatever value and Q of 0. You couldn't do that, right? That would not be possible.
Yeah, that would not be possible.
Right? So then there's only one, let me just say, one set of values of P and Q that are possible.
No. See, you have these two equations. P is this. So m cos alpha is a variable, m sin alpha is another variable. You solve these two equations for m sin alpha and m cos alpha. You get m and alpha.
So you can only get P and Q for solutions of those two equations.
Yes, correct. Yeah. So the
so the P and Q we can select are restricted.
yes.
values, yeah.
Restricted so that they get solved by these two equations. So 5000 watts and 400 VAR is possible.
Yeah.
Yeah.
What would you do if, like, you were in a larger system and you had a fixed VDC?
And a given load and
Yeah.
for that power, all you can do is reduce the modulation index.
Okay. And the phase angle. What you produce at the output is in your hand, right? Because from this MMC,
Yes, sir.
within limits, you can change the amplitude, and you can also change the phase angle at which that voltage is produced, such that for a given load, P and Q are simultaneously satisfied.
Yes, we have 2 variables and 2 equations to solve. So M is a variable, alpha is a variable, and solutions to these equations, the corresponding P and Q is possible. Yeah.
So you showed those 2 equations.
Yes.
And clearly you have 2 equations. So what Abhijit said, you think about what he said.
Yeah, Q cannot be 0. That's right. It cannot be any arbitrary P and Q.
Yeah. But given P and Q, you can find amplitude and angle.
Yes, sir.
Right?
So we can find MA and alpha, but maybe it will be out of range of the. See, MA may be greater than 1, which is not really feasible. So, feasible solution. So P and Q for feasible solutions should be okay.
Okay. This is an extremely useful topology for high voltage DC transmission. This is perhaps the way to go, right?
Okay. So the next question is initial capacitor voltage selection. Okay. This is useful because we know what the net voltage is produced in the arm and how the DC link current is produced as a function of the leg parameters, net voltage in the leg and leg parameters and things like that. So, then in this simulation I have a fixed current source here, which is of the value of 37.5 ampere peak and with 180 degree phase shift. That means the current is actually flowing out. The current is flowing out, it means MMC is feeding power to the load, so it needs to take current from the DC link. The current direction will be into. So if it feeds power out like that, DC link current would flow like that. So here I is flowing out into the load, and so the DC link current direction is that way, and we need to find out what the final average voltage of the module capacitors will be. That is the question. So if you choose the initial capacitor voltage to be close to the final average voltage that the simulation finds out to be, then the time, see, so if I run this, so VC average in steady state equals what? That is the question. So I have a IG of 37.5 ampere peak. I will modify this diagram here. This is a very high resistance just for the circuit to be able to solve. This current is 37.5 by root 2 angle 180 degrees in phasor quantity. Okay, that means the current is actually flowing out and the power is fed by the MMC to the load. What else do we have? We have R arm to be 5 ohms, L arm to be 0.5 millihenry, and then we have VDC to be 5000 volts. Yeah. So First of all, what do you think decides VC average? No, before that, what is the? Can you tell me what the net voltage is across this leg, ignoring the drop across? Ignore the drop across the arm inductors and resistors. So, what will be the net voltage produced in the leg? What is it?
Is it 5,000?
5,000. It should be 5,000. But yeah, but how did you get 5,000?
VDC.
VDC. Okay, so you mean this net voltage equals this net voltage? If that is the case, then there won't be any IDC, right? There should be some IDC flowing into this leg for power balance. So, do you think the net legs voltage will be somewhat less than 5,000? It will be somewhat less than 5,000, and so that is fine. So we know that V leg is approximately 5,000, and in fact it is less than 5,000. So how do we get V leg? What is it the sum of? It is, don't you think it's the sum of the sub-module output voltages? See, this voltage plus this voltage plus this voltage plus this voltage. So
define V leg.
V leg is this volt. V leg is this voltage.
Is it VU plus VL?
It also includes arm inductor resistor drops, but for now, no, I got the question. So V leg is VU plus VL. Yeah. So
You should have down.
yeah. So V leg is VU plus VL. So we know VU is like this, and VL is like this. So it's not VDC by 2 actually. It'll be something less than VDC by 2. So V leg in
So in those plots, Vishnu, where is the zero axis?
this is 0. So VU is 0.5 times VC average times N. Plus the sinusoidal part of the submodule output voltage, but I add VL to it, so I cancel the sinusoidal part. So what I am doing is I am adding VU and VL, and then the sinusoids are 180 degree out of phase with each other, because we know output voltage is VL minus VU by 2. We have seen these graphs, right? So the sinusoid reference for the upper arm is 180 degree out of phase with the lower arm, and this sinusoidal voltage is a result of N times MA times VC average. So I can write this as N times MA times VC average, or VU is minus MA, so this is minus MA times VC average plus 0.5 times VC average times N plus N times MA times VC average. What is MA? MA is so M is 0.5 plus MA sin omega t plus alpha. We saw this. So I was calling this as MA. Maybe I need another notation. Let's say this. Is that clear? So then, what is VU plus VL? It is VC average times N. Okay.
And N is the total number of submodules.
Submodules in an
Four
arm.
here.
In an
N
arm.
is equal to 4 here, right?
Yes. No. N is submodules in an arm.
Okay. So N is equal to 2.
2 in this picture.
Right. Now that's what I would have thought. So VC average is really 5,000 roughly divided by 2,
Yes, sir.
right?
Yes, if you have 4 modules in a lake.
So you just can't take 5,000 and divide it by 4.
No, they know that. We talked about that, right? The sum of the modules in an arm should be equal to DC bus voltage. Some module voltage in an arm should be equal to DC bus voltage to produce a symmetric sine wave.
But so the point I'm wrestling with, Vishnu, is that if you take the capacitor voltages,
Yeah.
right, and you multiply with the number of capacitors you have, you get twice the DC voltage.
Yes, sir. Correct.
You'll get 10,000,
Yes.
right? Because some of them are not there
Yeah.
when you synthesize, right?
Yes, sir.
Okay, so you have negative and you have positive. Some of the modules is not there,
Yeah. Correct.
right? So you can't have that one module missing.
And
So that's why it leads to that.
yes. So the average voltage at the output of each submodule is 0.5 times its DC bus voltage. So 0.5 times the DC voltage, sum of DC voltage of submodule should add up to ADC. So that's what this is. So we have DC average times N is VU plus VL. And let me call that V leg. So V leg doesn't include the arm inductor. So let me forget about V leg. Let me just keep it as N times VC average. We'll go with that quantity. So yeah. So what is IDC now? So first of all, the average voltage across the inductor is 0 in any power electronic circuit, right? So ignore the DC voltage in the arm inductors. So we have IDC to be VDC minus N times VC average by R arm times 2. Do you agree with that? So what does it mean? The DC link current is only limited by the arm inductors and the difference between the sum of capacitor voltage and the DC bus voltage. So we have this equation, and then we are in a quest to find out VC average. So we know that VC average influences IDC. What else is IDC influenced by? We know from upper arm power equation that the net DC power absorbed by upper arm should be 0. Right? We saw that last class. So then what is the power absorbed by the upper arm? So power absorbed by the upper arm. So I am only looking at the power absorbed by these two submodules in this case here then. Not looking at the power absorbed by the arm resistor. So net power absorbed by the upper arm meaning upper arm submodules. Upper arm submodules alone. So what will that be? That will be the voltage produced by the upper arm, which is N times VC average by 2. N is the number of submodules, and we know N is the number of submodules. N is the number of submodules per arm, and the DC voltage is 0.5 times VC average of each. So 0.5 times VC average of each times N. That's the DC voltage. Okay. Plus we have N times MA times VC average. So that's the voltage in the upper arm times I have IDC. So my current direction, this is IG flows into the MMC. So the upper arm current will have an IDC and minus half of IG. Why is it half of IG? Because average voltage produced by upper arm and lower arm is the same. We talked about this. So I have IDC, so minus IG over 2. Okay, is that what I have here? M times, yes. Yeah, that's what I have there. So then let me put in numbers for these things. I have this to be equal to, I have 4 submodules in my simulation per arm. So I have 4 times, this is PU, and we know that the DC part of this, if you extract the DC power components of this, the sum of that should be 0 because it shouldn't absorb net DC power. So I have, what is the DC power quantities here? It is NC average by 2 times IDC, and then these two components interact to give this net DC component. So real part of, so I know MA tilde is MA sin omega t plus alpha. So real part of, it's better I just copy it from my note.
Have they seen these equations?
Yeah, they saw this equation, PU, that's all we need. And so n times VC average by 2 times IDC plus real part of, and in the upper arm the modulating signal is 180 degree phase shifted from lower arm, because VL minus VU by 2 is output voltage. So VU has 180 degree phase shifted modulating signal. So this should be minus MA. So times IDC plus real part of, let me put in the numbers in the simulation. So N is 4 in the simulation, 4 submodules per arm. So I have, so equating the DC power out of this, I have 4 times VC times 0.5 times 5000 minus 4 VC by 10 should be equal to real part of minus 4 VC by root 2 times 0.42 times angle 20 degrees times 0.5 times 37.5 by root 2 angle 180. What is that equation? So N times VC average by 2, so that is this part, times IDC, this is IDC, DC bus voltage minus 4 times VC by 10, 10 is 2 times R amp, so that is this equation right here, this is IDC equals real part of so this times this, if it is minus here, becomes plus, and I need to equate the sum to 0, so that goes to the right side as minus here. Equate the sum of DC powers to 0 here, and this part, if you take it to the right side, becomes minus here, and 4 VC by root 2 is the phasor quantity in phasor RMS. This is MA, this is So do you know how I got 0.42? In my simulation, the modulation index m dash was 0.84. So if I convert it to m equals 0.5 plus ma tilde, what should I do? I should multiply this by 0.5 and uh, add 0.5. So that is in this form. So ma tilde has a peak amplitude of 0.42. Okay, let me say that again. M dash in my simulation is 0.84 and m is what? M dash times 0.5 plus 0.5 and this is ma tilde. Do you get that? So ma tilde has a peak amplitude. So this is actually 0.42 sine omega t plus alpha. So I have so this in phasor quantity is this 0.42 times so n Vc average is here 4 Vc, 0.42 by root 2, that is a phasor. Angle of alpha is 20 degrees, this is alpha, times this is peak of Ig, so in phasor quantity that will be by root 2 and it has a phase angle of 180 degree in simulation. So that is that. So then if you solve for Vc from this, all you have to solve for from this is Vc. You get Vc to be 1231 volts, and you see that in simulation.
Vishnu,
Yeah.
so for phasor representation,
Yeah.
why is the one VC average is divided by root 2 and the other one is not divided by root 2?
Here,
Yeah.
this is not phasor. These are all DC quantities. Only AC quantities have phasor, meaning of phasor, right?
On the right side as well, n times VC average term, only that MA term has your phasor, right? Or
Yeah. So yeah, you can say by root 2 here. Okay.
Vishnu, I have to go, but we should write this up very clearly as a homework problem, right? So we can work on it together
Okay.
and hand it out on Thursday, based on the equations that you have described in this here. But I have a question here, that the current that is coming from the DC bus voltage must have a very large ripple, right? Right? Because what you're writing is the DC component of it,
Yes, sir.
with that thing you have in the box,
Yeah. So
right below.
yes, sir.
In your,
Yes, sir.
you know,
Yep.
this one here, right?
Yeah. So we are assuming the circulating current. We are neglecting the circulating current in this equation because it doesn't contribute to DC average power. In the next step, we are only interested in DC average power. And we use this equation to find out the origin of second harmonic current last time. That assumed we did not know that there was a second harmonic circulating current to start with, and then second harmonic circulating current resulted due to this basic power equation. So yeah, in these calculations I only assume that circulating current consists of IDC, and that is sufficient to find out DC power because other components don't contribute to DC power.
Just one clarification.
Yeah.
So this is for one phase, right? So that's why it seems like it has large ripple. But in three phase, what will happen is that the three phases they are offset, so they
Sure.
cancel out and you get DC on the DC, right?
Yeah. But you know, you just stay with this single phase circuit,
Yes.
right? Then you have large ripple, just
Yes.
like in a single
Single
phase
phase
rectifier, right?
Yes.
Uh,
All right, Krishna.
So yeah, if I run this simulation, so you see that Ig here is 37.5 ampere peak, 180 degree phase shift, and R has a resistance of 5 ohms, and then if I open the capacitor voltage waveforms, so if you put any other initial voltage as against 1231, it will take a long time to settle to 1231 volts. So what I mean is the capacitor voltage is here an approximate average 1231, 1231.5 maybe. But if you put the initial voltage to be 1250, then the simulation will converge to 1231. So if you want quick steady state, you start with the correct initial voltage. The initial voltage is much different from what we know, which is 5000 by 4, because these arm resistors are big. They are 10 ohms. If they are negligible, then the initial capacitor voltage will approximately be 5000 by 4. So what did we learn here? We learned that the sum of the submodule voltages is n times VC average, and that plays a role in net DC link current. And DC link current also plays a role in the net power of DC power absorbed by PU to be 0. If you take the DC, we expanded this last time. So if you equate the net DC power to 0 and substitute for Ig, you get VC out of this. So I think 2 questions are sufficient, don't you think? Should I go to the third question? Yeah, I think we'll stop with this. And then I'll write out 2 questions and give it. Oh, and yeah, let me talk about the modifications that we need to do in these files. So the first thing that you need to do is open all the submodules, open all the submodule blocks, and set Ri, Ci, Vc all to default values. Some modules will be multiplied by 1.05 and some factors. You see what I mean? Some modules will be multiplied by Ci times 1.05 or Vc times 1.02. Set it all to this same values, Ri, Ci and Vc. Do you know where Ri, Ci and Vc are? It's in this model here. Init files. Init files have Ri, Ci and other parameters. Okay. And then the next thing that you need to do is for the first question, set R-arm and L-arm to be, don't change the value of L-arm ever, keep L-arm whatever is default in the model file that's given to you. But for this question, set R-arm to be 0.1 ohms. For this question, set R-arm to be 5 ohms. We should write this out in the assignment, but you should know that you should open these things and change R-arm here from 0.1 to 5 for the second question. And then for the first question again, you need to change these values, right? R out and L out. In the simulation that's given to you, you will also have an AC source. Delete the AC source and set R out and L out to the value given in the question. That will be 50 ohms and R out will be 50 ohms and L out will be 10 millihenry. Set those to that value, and then what else should we do? Oh yeah, and then an important thing. Do you see this yellow block here? There are 2 yellow blocks, and upper control signals usually go through this control path. It is summed, and the net sum pulse is taken, given to the balancing block and redistributed to the submodules. We talked about this briefly. What you should do is bypass this, connect the upper control signals directly to this mux here. Bypass the voltage balancing and sorting circuitry. So in the assignment, all you will find is bypass the voltage balancing and sorting circuitry. What you should do, what that means is connect upper control signals to the mux, lower control signals to the mux again directly here. Okay, keep that in mind. Then, what else should we do? And then you can connect scopes wherever you want. You know how to connect scopes, right? You go to Simulink library browser, syncs, and there is a scope here. Just drag it and drop it here. This is to view the waveforms. You can put the scope anywhere you want and connect the signal to that. And then, yeah, it would have been nice if you had your laptop so you could have done it together. But yeah. What else should we do? Yeah, so for the first question, you remove the AC source and connect R out and L out. For the second question, what will you do? You do this. Remove R out, L out, AC source, everything. Just connect an AC current source. AC current source, like this, feeding into the MMC and the large resistor in parallel with it, say 500,000 ohms. And
Are you going to give us this file, or are we going to need to modify it?
yeah, you have to modify.
Okay.
So in the question, it will be written, and a constant AC current source is connected at the output of this amplitude, 37.5 amperes peak, and that phase shift. That means what you have to do is you have to go to SimScape and search for the source. In SimScape, power systems and sources are not there. Specialized technology, fundamental box, electrical sources, and AC current source. It's here. So drag and drop this block like that, and you have the AC current source. Maybe I can give the two files. But yeah, I can give the two files, but and then you show the analysis, which again I showed on the board. So I'll give the two files, and if you have copied what we did on the board today, carry out the calculation and see that the results and your calculation matches, it should be fine. I'll give the two files, that's better. Yeah, that's it. I wonder if I should dictate the questions or write it out.
You should write it out because
Unite people should be listening too, right? So if I dictate the question, then you can ask me clarifications here itself.
I mean, I'd rather have it written out.
Okay, I'll write it out. Yeah, two questions, I'll write that out and send these two simulation files. That should be it. Okay, thank you.
Did you finish the whole thing?
No, not yet. I'm not convinced I'll be able to figure out the first question. The second one, I think I will, and I got the third and fourth.
Alright, what did you think of homework 4?
I thought, I wasn't really sure.